Let's look at the Fourier series for f of x equal to x square. We know the Fourier series formula is this. To be able to apply this to this function, we have to figure out what is a naught, an, and bn. So let's proceed to find a naught, an, bn. Now, in the previous session, we saw a naught is equal to 1 by pi times integral from minus pi to pi of f of x dx. So a naught is equal to 1 by pi times the integral minus pi to pi of x square dx. And we know that the integral of x square is x cubed by 3. And we have to figure out from minus pi to pi. So we have a naught is equal to 1 by pi times x cubed by 3 from minus pi to pi, which is equal to 1 by pi times pi cube. So we substitute x with pi. So pi cube by 3 minus. Now we have to substitute minus pi. So minus pi cube by 3, which is equal to this minus minus cancel out because minus pi cube is minus pi cube. We end up with 1 by pi times 2 pi cube by 3. Pi and pi can get cancelled. So we are left with 2 pi square by 3. Now we have to figure out an. Again, from the previous session, we know an is equal to 1 by pi times the integral from minus pi to pi of x square times cos nx dx. We apply a trick here. We say an is equal to 2 by pi times the integral from 0 to pi of x square times cos nx dx. So basically what we are doing is, instead of taking from pi minus pi to pi, since it is symmetric, we are saying 0 to pi, we are taking, which is half of minus pi to pi, and we are doubling the integral. Now let's apply this. We get an is equal to 2 by pi times, and this is where we need to apply integration by parts. So what is that? So if u is equal to f of x and v is equal to g of x, then integral u times v times dx is equal to u times v1. So here u is the function itself. v1 is the first integral of, or the integral of v minus first derivative of u times the second integral of v, or the integral of v1 plus the second derivative of f of x times the third integral of v, or the integral of v2. And like this, we keep doing it till we end up with 0. And we have to choose which of these will be u and which one will be v. So here we know x square is going to, on successive differentiation, will become 0. And cos nx will never become 0 on successive differentiation. So accordingly, we take u as x square. So let's apply this. U as it is, so x square as it is. Integral of cos nx, which is sin nx, divided by n minus, now the derivative of x square, so 2x, times the integral of sin nx, which is minus cos nx by n square. Now the second derivative of u, or the derivative of 2x, which is 2, times the next integral, that is the integral of minus cos nx, which is minus sin nx by n cube. And now if we again go to the next term, what will happen, that when we differentiate 2, it will become 0. So the whole thing will become 0. So we stop. And now this we have to evaluate from 0 to pi. So when we do that, what do we get? An is equal to 2 by pi times, first we substitute pi. What happens? Sine pi is 0. So the first term becomes 0. What happens when we substitute pi here? 2 pi times minus cos n pi. So minus minus becomes plus. So we end up with 2 pi times cos n pi by n square. Minus, again, sine pi is 0. So here it becomes 0. Minus, now we have to repeat that step with 0. So this becomes 0, this becomes 0, this which will also be 0 because sine 0 is 0. So an is equal to 2 by pi times 2 pi times cos n pi by n square, which on simplification becomes an is equal to 4 times cos n pi by n square. So now we have an. Now again from the previous session, we know bn is equal to 1 by pi times integral from minus pi to pi of f of x times sine nx dx. Now let's apply that. We get bn is equal to 1 by pi times minus pi to pi of x square times sine nx dx. And that works out to 0. So we have found a naught, we have found an, and bn we can ignore because it is 0. Let's apply this into the Fourier formula. So f of x, which is x square, is equal to a naught by 2, which is 2 pi square by 3. So we get 2 pi square by 3 times 2 plus summation as n goes from 1 to infinity of an. An is 4 times cos n pi by n square. So 4 times by n square we have written. Now cos n pi seems to have disappeared. No, actually it has not. Minus 1 to the power of n is cos n pi. Because when we say cos pi, it is minus 1. Cos 2 pi is 1, positive 1. Cos 3 pi is minus 1. So that has been converted into minus 1 to the power of n times cos nx. And finally plus summation as n goes from 1 to infinity of 0. This we simplify to f of x equal to x square, which is equal to 2 cancels out, pi square by 3 plus 4 we can take it out, 4 times summation as n goes from 1 to infinity of minus 1 to the power of n times cos nx by n square. Okay, now let's expand it. So we have f of x equal to x square, which is equal to pi square by 3 plus 4 times. Now take it one by one. So when n is equal to 1, minus 1 to the power of 1 is minus 1. So minus n square, 1 square is 1 times cos x is cos x. Now when we take n equal to 2, what happens? Minus 1 square is plus 1. 2 square is 4. Cos 2x. Again, when we take n equal to 3, we get minus 1 to the power of 3, which is minus 1. So minus cos 3x by 3 square, which is 9. Like this, we keep doing it. And the sign keeps alternating. So this is the Fourier series for f of x equal to x square. And this we had seen in the first session. Okay, now let me just demonstrate this again. So I'm going to draw the graph of pi square by 3 minus 4 cos x, just with the first term. This is the graph we get. Now when we take 2, that is the first 2 terms, we get pi square by 3. This is the graph for pi square by 3 minus 4 cos x plus cos 2x, because 4 and 4 cancel out. Similarly, when we take 3, m equal to 3, we get pi square by 3 minus 4 cos x plus cos 2x minus 4 by 9 cos 3x. So as I keep increasing the terms, the graph converges with f of x equal to x square. Interesting result. If x is equal to 0, then we get f of 0 is equal to x square. So 0 square, which is 0, equal to pi square by 3 plus 4 times what will happen? Cos 1x, 2x, 3x, they all become cos 0. Cos 0 is 1. So we are left with minus 1 plus 1 by 4 minus 1 by 9 and so on. Let's rearrange it. Since this expression is equal to 0, we take pi square by 3 to the other side. So it becomes minus pi square by 3. Then we take 4 to the other side. It goes into the denominator. So that we end up with 1 minus 1 by 4 plus 1 by 9 minus and so on is equal to pi square by 12. And in summation notation, it can be written like this. A very interesting result. A series is ending up with a pi. That's the interesting part, because usually pi is associated with a circle. But of course, now we know how we arrived at this. So let me again remind you, there is a link to a PDF book which describes all these in detail. Please feel free to download it, refer to it. And if you think somebody else can also benefit from it, please do share. That's it for now.